So there's one last thing we need to go over in this unit, and that is a couple of different applications that we can, or some word problems we can solve with these differential equations. So one type of function that you've worked with before, like going all the way back to like algebra 1 and before probably, is an exponential function. And one thing that's true about an exponential function is that it grows at a rate that is proportional to its value. So you think about what that means. Okay, grows at a rate that is proportional to its value. Meaning there's some scale factor that you could multiply an exponential function's value by to get its rate. Okay, so one way you can kind of think about this is within the context of, like, let's say you're investing some money. Yeah. Well, there's an old phrase that says it takes money to make money. Yeah, and that's true in the context of investments, because if an investment's going to grow exponentially, it will grow a lot faster if the investment is bigger. Okay, if you invest more money, it will grow faster. If you invest a little bit of money, it'll grow by a little bit. Okay, and that is because the rate of growth is proportional to the value in an exponential function. So let's take a look at it, sort of like a word problem here that we could solve with that idea in mind. So number 1 says, consider an investment where the rate of investment grows, or where the rate of your investment grows. Okay, the grammar's kind of messed up there. Grows at? I don't think we need that word at in there. Is proportional to the value of the investment. Number 1, determine a differential equation to represent the problem. So let's try to break this down. We've got an investment. Okay, we're looking for a differential equation. So we're looking for an equation for the rate. Okay, the rate of your investment. That is what we are solving for. Okay, that is a derivative. Rate is like your slope. And we are going to have to declare some variables here. So let's call the investment capital I. Makes sense for investment. Yeah, and let's let the time that we're measuring the value of this investment over, t. So if that's the case, then the rate of the investment's growth is di over dt. Right? The rate of the value of the investment with respect to time. Now, the fact that it grows proportionally to the value of the investment means that, the value of the investment, that's our I. But the fact that the rate is growing proportional to that means that there is some scale factor that you could multiply the value of the investment by to get the rate. Yeah, that's what it means to be proportional. You could also say there's like a direct variation here. So let's set this up. We've got our differential, the derivative of the value of the investment with respect to time is proportional. Now we need to give a name to this scale factor, for lack of a better word, but it will be a constant, okay, because it is proportional. So we'll call that constant K. So K times the investment. So in other words, there's some scale factor, some multiplier that you could multiply the value of the investment for any value and figure out what the rate is. Okay. So part B, so that's it. That's your equation. Part B says determine the particular solution. Okay, remember, particular solution just means that we're going to have to find the C eventually. Given that you initially invest $1,000 and your investment grows to $1,500 after 10 years. So what we're implicitly given here are two coordinates on our function for I. And that's what we want to find, okay? When it says determine the particular solution for your investment, what we're trying to do is solve for y, okay? So for this particular solution, we are trying to solve for I, okay, in terms of t. Okay, so that's the value of the investment. And whatever the function ends up being, they gave us two implied points here. It says you initially invest $1,000. That means when t is 0, the I value, the value of the investment is $1,000. Also, we know that the investment's worth $1,500 after 10 years. So 10, 1,500. So we've got those two given points. And now we're ready to solve for I. We want to get rid of the di and the dt here. But now we know how to do that. Yeah. All we need to do is separate the variables, integrate both sides, and solve for I, just like we've been doing. So I'm going to rewrite that equation down here. di over dt equals k times I. This is stating that the value of the investment is proportional to the rate at which it grows. Now, the I I'm going to need to move to the left. The k, remember, is some constant. We actually need to figure out what that k is, but we'll come back to that. This is different than the c that we'll get from the integration process. This k is the proportionality constant. So we need to move the I over here. We're going to move the dt over here. And we'll get I to the -1 di equals k dt. Now notice that there's no instance of the variable t on the right-hand side, right? So this is kind of like we have like 5 dt. So when we go to integrate that, since we're going to be integrating with respect to t, if this was just 5, it would become 5t. If it was 2, it'd become 2t. If it was just 1, it'd become 1t. For k, it'll become kt plus c. So yeah, let's go ahead and integrate both sides. On the left side, we're integrating with respect to the value of the investment. On the right side, we're integrating with respect to the time. So we know this integral, yeah, I to the -1. What's the integral of I to the -1 with respect to I? Yeah, natural log of the absolute value of the value of the investment. We're hoping that doesn't go negative, honestly. Yeah, that would be a bad investment. Equals, now k is a constant. Again, it's like 5. So if I integrate 5 with respect to t, that becomes 5t. So in this case, it would just be kt plus c. All right, so what do I need to do next? I'm trying to isolate I here. Yeah, we can take the, or exponentiate both sides. So we have the absolute value of I equals e to the kt plus c. And it may not yet be, but very soon, this problem is going to start making a little bit more sense and look a little bit more familiar to you. We're not quite there yet, but it should very soon. Okay, we need to decide, we're going to have a plus minus here. So is this going to be plus or minus? Plus, right? Because the value is always positive for all the information we have. So we're going to have I equals, and I'm actually going to write this E a little differently. So there is an exponential property that says that if you multiply, you don't need to write this part down, but if you multiply two powers with the same base, how do you combine those? A to the x plus y. You can add the exponents. But you can also take this property backwards. If you've got a power with a sum for the exponent, you can split that up. In other words, like if you have something in this form, you can split it up like this. And so I'm going to actually split this up as e to the kt times e to the c. And the reason why I'm going to do that is because e to the c is just some other constant. Right? Like if the constant was 5, e to the fifth power is just some other constant. So this is going to turn into our new c. With me?
So I equals kt plus c.
That's right. I is c times e to the kt. Okay. Now, again, to be very clear, this c is not the same as this c, right? This is e to the c, but that's just going to be a new constant that we'll solve for here. Now, this formula may not look super familiar as it's written, but you've seen this formula before, back in maybe pre-calculus, but for sure in Algebra 2. It probably didn't look like this, though. They probably wrote it like this. A equals P times e to the RT. It's the same formula. It's a continuously compounding investment. All right. So there's two constants here that we need to find. We need to find the C, but we also kind of need that K also. Now, if you remember back to Algebra 2, you had this formula. What did the P represent? The initial value is the principal, right? The initial investment. So we should expect C to be what? We should expect C to be 1,000. But you don't have to remember this to be able to figure that out. What you could do is just find it algebraically. Now, if you know that little shortcut, that would be pretty handy. But let's say you just forget the shortcut and you're like, okay, well, let's try to find that C value. And we can use the initial amount, this initial point, 0, 1,000, to find that C value. Because if the investment's worth $1,000, when T is 0, well, K times 0 is 0. E to the 0 is 1. So 1,000 equals C times 1. Again, if you remember back to Algebra 2, this initial investment should be this coefficient of the exponential function. So that sort of checks out, yeah? So right now we've got an equation. I equals 1,000 times e to the kt. Now we're looking for that particular solution. We're really looking for an equation here that could give us the value of the investment at any time. So we still need to find that k value. So let's find that k value. We can find, now we have we've got C filled in here. We could use the other given information, the fact that it's worth $1,500 after 10 years, and plug in 10 into T and 1,500 into I to solve for K. So 1,500 equals 1,000 times e to the k times 10. All right, so now we just need to do a little algebra. Kind of go back to algebra 2 a little bit more here, solve for that. We need to divide both sides by 1,000, which will just be 1.5. E to the 10k. And if we want to try to isolate that 10k, try to get rid of that exponent or that base of e, we need to take the natural log of both sides. So k will be the natural log of 1.5 over 10. Now, if this were on a calculator portion of the test, you'd want to estimate that. You just throw it in the calculator, but I'll leave it in exact form so you don't have to break out the calculator. But yeah, let's go ahead and write our final answer here. I equals 1,000 times e to the power of natural log of 1.5 over 10 times t. You could use a calculator to estimate that, but you might as well just leave it in exact form for right now. Oh, yes, 1,000. I dropped a 0. Yeah, thank you. Any questions about what we just did there? All right, so the follow-up question here is how long will it take for the initial investment to double? So if it was initially worth $1,000, we're interested in when it's worth $2,000. So we're going to say 2,000, and we want to find the time. So 2,000 equals 1,000 times e to the power of natural log of 1.5 over 10 t. And now we need to solve for t. So we'll divide both sides by 1,000 and get 2 equals e to the natural log of 1.5 over 10t. At this point, we need to take the natural log of both sides. So we have natural log of 2 equals the natural log of 1. Maybe I'll rewrite this so I don't have a fraction there as 1/10 times the natural log of 1.5 t. And here I could multiply both sides by 10, divide both sides by the natural log of 1.5. So I get 10 natural log of 2 over natural log of 1.5. And that's going to be the number of years. Now, I would imagine this problem might be a calculator question. So, because if we want any kind of useful answer here, like if I say, hey, you go to the bank and you're like, hey, I want to make an investment. How long is it going to take for my money to double? They're going to say, yeah, it'll double in about 10 times natural log of 2 divided by natural log of 1.5 years. That's not very helpful, right? So yeah, let's see how many years that is. 10 times the natural log of 2 divided by the natural log of 1.5 is about 17 years. Any questions so far? All right, let's do one more problem that's very similar to this, but we'll kind of speed run the next one, okay? All right, so another one of your investments also grows proportionally to the money in the investment. It says you initially invest $250. So we have an implied coordinate here, 0, 250. 10 years later, the money has grown to $350. The question here is, how much money will you have in 25 years? Assuming you don't add any extra money. Just let the money grow. So if we start with that exact same equation that we did before, and we go through the exact same separation of variables and integration, and we're going to end up with the exact same equation. So you could just, see your work on problem number 1 to see where this formula is coming from. But again, it's just that A equals P times e to the RT equation. We also noticed that the C value is the initial investment, because if T is 0, this equals 1, and so it's just 1 times C. So what's the C value? 250. Okay, that's right here. This is the C value. So if I equals 250 times e to the kt, and now we can find k. All right, so to find k, we can use the other piece of information, the fact that it's worth $350 after 10 years. Substitute that into t and to I to solve for k. So 350 equals 250 times e to the k times 10. And we'll solve this basically exactly like we did on the last problem. Divide both sides by 250. It's 3.5 divided by 2.5 is 1.4. So you get 1.4 is e to the 10k. Then we can take the natural log of both sides. So the natural log of 1.4 is 10k. So k is the natural log of 1.4 over 10. All right, now we got k. All right, so I equals 250 times e to the natural log of 1.4 over 10t. Now we've got a particular solution. So ultimately the question's asking how much money will you have 25 years after you make the investment. So now that we have our particular solution, we can just substitute in 25 to get our answer, right, into t. And obviously this is something you'd have to put in the calculator. You wouldn't be able to really calculate this by hand. So what would this be? Let's see. Natural log 1.4 divided by 10, 25. Where's the e on here? Okay, so I get approximately $579.78. All right, any questions about these investment problems? Yes, ma'am.
What does the I stand for?
The value of the investment. So I for investment. You don't necessarily have to use that letter. I just picked it because it was the first letter of the word. Yeah. But like in algebra 2, you would have called that A. for like final amount.
And what does the I stand for?
So that's the proportionality constant. That's the constant that basically that relates the rate of growth to the actual value. All right, you guys ready for another one? All right, let's move on to number 3. Okay, and these are just coming from old AP problems, yo. The rate of change of volume of water is a certain tank. Wait a minute. In a certain tank. There are just typos everywhere here. The rate of change of the volume of water in a certain tank with respect to time is directly proportional to the square root of the volume. So not just the volume, but the square root of the volume. So the rate of change, that's dV of volume with respect to time. Right? Instead of like change in y over change in x, this is change in v over change in t. Is proportional to the square root of the volume. So there's your differential equation. And now it says, given that the tank initially has 25 gallons of water, so if it initially has 25 gallons of water, then we have this 0.0, 25, and has 49 gallons of water 3 hours later, we've got a 0.3, 49. We could determine an equation that models the volume of water in the tank. Excuse me. In other words, solve for V. So we'll start with our differential. And this is going to require that we separate the variables. This is a separable differential equation. So we'll get the t over to the right and the v over to the left. Now this one will work out a little differently than the last couple because this is not just v, it's square root of v. So if we divide both sides by square root of v, that'll be like the square root of v to the negative first power. Square root of v is v to the 1/2 power. 1/2 times negative 1 is negative 1/2. So we've got v to the negative 1/2 dv equals k dt. So now we've separated the variables. Now we can integrate both sides. And here we're not going to have a natural log, right? Because this power is not negative 1. So we could just use the regular old anti-power rule. You can increase that exponent by 1 and then divide by the new exponent. So negative 1/2 plus 1 is 1/2. So we end up with square root of v here. So square root of v divided by negative 1/2, or positive 1/2. So dividing by 1/2 is the same thing as multiplying by 2. That'll equal kt plus c. Then we could divide both sides by 2. So we get square root of v equals, what would that be? K over 2t plus c. Now this is probably going to be a good equation to solve for c once we're ready for that, but let's come back to that.
Why don't we just do 2 divided by 2? Why did it just say?
Oh, it's like this whole term is divided by 2, so you're like multiplying these two numbers and then dividing by 2. So you're only dividing by 2 once. So basically you've got 3 factors. You've got 1/2, k, and t. And you can group those however you want. Yeah. It's just that, like, instead of having like 2x over 5, sometimes it's easier to write it as like 2/5 x. Yeah. Yes, ma'am.
How did the
So K is like a constant. So imagine you had like integral of like 2 dx. This would just become 2x plus c. Right. So that's pretty much exactly what's happening over here, except so K is just some unknown constant. It's not the variable that we're integrating with respect to, so you're treating it as a constant. Okay, and then so, yeah, like what function has a slope that's this constant? It would be that constant times the variable. All right, so finally we're going to square both sides. So we have V equals K over 2t plus C quantity squared. So that would be like our general solution, but we're going to need the particular solution. So we need C and we need K. Now first it says that our initial initial volume was 25 gallons. So if I plug in 0 here, 0 here, and 25 here, we're going to be able to find C pretty easily here. Right, so the volume's 25. Then we have K over 2 times 0, so that's just all 0, plus C squared. So yeah, what's the square root of 25? 5. Yeah, so C is going to be 5. So now we've got V equals K over 2t plus 5 squared. But now we need K. So this is where we'll use the other coordinate. The 3, 49. The fact that it's got 49 gallons of water 3 hours later. So 49 equals K over 2 times 3 plus 5 quantity squared. So we'll take the square root of both sides. We've got 7 equals 3 halves K plus 5. Then we can subtract 5 from both sides. We get 2 equals 3 halves K. And then we're going to multiply both sides by 2 and then divide by 3. So K is 4/3. So now I think we've got everything we need. The volume is, let's see. So if K is 4/3, we've got, let's look back at this equation. 4/3 divided by 2. 4/6. What does 4/6 reduce to? 2/3. So 2/3 T plus 5 squared. And that should give you the volume with respect to time. Now you can always, if you're, there's obviously a lot of algebra, a lot of calculus going on here. If you're not like 100% confident in your answer, what I would suggest you do is just go back and plug in both of these points and verify that they are in fact solutions to this equation, which I think you'll see that they are. Any questions so far? Okay, one last problem. The growth rate for a population of fruit flies is proportional to the number present. So you've got another one of these situations where the rate is proportional to the value. The initial population was 100 flies. So that means we've got this coordinate 0, 100. And 4 days later, there were 500 flies. So if we're solving for P in terms of T, we know that the rate at which the population is growing, which is dP dt, the derivative of the position with respect to time, that's the rate of the population's change with respect to time, is proportional to the population. All right, so we want to separate our variables, integrate, go from there. So dividing both sides by p is going to give me p to the negative 1 dp equals k dt. Now we can integrate both sides, and this integration is going to be should be pretty familiar from the last few problems. It's going to give us the natural log of the absolute value of p equals k times t plus c. All right, to undo that natural log, we're going to exponentiate, get the absolute value of p equals e to the kt plus c. We're going to do kind of the same thing we did on the investment problem. We're going to split off this e to the c and make that a new constant. Also, the population can't be negative, right? So this has got to be a positive number. So p equals e to the kt times e to the c, or c, this new c, times e to the kt. So it's just the old PERT formula again. They're all just exponential functions. Yeah. Okay, so we've got two things we've got to find. We've got to find our c and we've got to find our k. So first we'll find c. Now, if you've been following along, you shouldn't have to do the algebra. What should c be? Yeah, it should be 100, although we can verify it if that's not immediately obvious to you, by simply plugging in that coordinate. Okay, 100 equals c times e to the k times 0, but hopefully you see why it's 100. That was pretty bad. Okay. Again, that should just be, this coefficient should just be your initial amount. Okay, and then we'll find k. And we could use the other point to find k. So we've got 500 equals, now that we know c is 100, we could throw that in, 100 times e to the k times 4. Divide both sides by 100, get 5 equals e to the 4k. Take the natural log of both sides, and divide both sides by 4. So we get the natural log of 5 over 4 as our k value. Yes, ma'am?
Can you explain again
Yeah.
how e to the kt times e to the c is becomes c e to the kt?
Yeah. So are you okay with this step?
Yeah.
Okay, that's using that exponent property, right? So this e to the c is just some constant. E is a constant. It's like 2.7 something. C is defined as a constant. So when you raise like a constant to a constant, let's say like 2 cubed, you end up with a constant. There's no variable being in there. So we're just like giving that constant the name c. So this c is not the same as that c. And we've seen that in these problems before, like not in this particular one, but like ones we've done before where like you divide both sides by 2, right? And the c like doesn't change, right? It actually does change. We're just not keeping track of those changes because ultimately we're just going to fill this in at the end anyway. It'll just be a lot easier to solve written like this. All right, so let's write our equation. P equals 100 times e to the natural log of 5 over 4 t. So we can use that, and we'll use a calculator for these next couple problems, but we can use that to find the population after 10 days. And, when will the population be 1,000? So after 10 days, we're just going to substitute in 10 in for t. So 100 times e to the natural log of 5 over 4 times 10. I'm going to have to type that in. So 100 times e to the, 10 times natural log 5 over 4. Okay, so it's approximately 5,590 flies. And finally, when will the population be 1,000? Here we're going to set the equation equal to 1,000 and solve for t. So we've got 1,000 equals 100 times e to the natural log of 5 over 4 times t. And we're solving for t here. So first we'll divide both sides by 100. So 10. Then we'll take the natural log of both sides. Hopefully you can see algebraically where this is going. And I'll write that as actually 1/4 natural log of 5. Just make it a little bit more obvious what's going to happen here. Then we need to multiply both sides by 4 and then divide both sides by natural log of 5. So we get 4 natural log of 10 over natural log of 5. That's our t. This is in terms of days. So if we want to actually get a better answer there, something that's a little bit more understandable, 4 natural log of 10 divided by natural log of 5 is roughly 5.722 days.